All right, welcome to the GOA-ON webinar series. I see people are being admitted in, so we'll start in just a moment. All right, looks like we've hit a little bit of a plateau in numbers. So welcome everyone to the GOA-ON webinar series, and thank you very much for joining us. My name is Kalina Grab, and I'm a GOA-ON Secretariat and a Knauss Fellow at NOAA in the Ocean Acidification Program. And I will be introducing the webinar for you today. So this webinar series has 4 supporting organizations. First, GOA-ON, which is the Global Ocean Acidification Observing Network. Second, NOAA, the National Oceanic and Atmospheric Administration. Third, the IEA OAICC, which is the International Atomic Energy Agency Ocean Acidification International Coordination Center. And the IOC UNESCO, which is the Intergovernmental Oceanographic Commission for the United Nations Educational, Scientific, and Cultural Organization. So for those of you that are not familiar, or for those of you that are new to GOA-ON, it is a collaborative international network of over 1,000 members from 105 countries. It is designed to detect and understand the drivers of ocean acidification and the resulting impacts on marine ecosystems. So during these presentations, all participants will be in listen-only mode. You are welcome to type any questions into the question box, which can be found at the bottom of the control panel on the right-hand side of your screen. And we'll be monitoring incoming questions, and we'll pose them to our speakers during the question and answer section, which will begin immediately after the last presentation. So at this time, I'd like to introduce the moderator for today, Dr. Richard Feely. So Dr. Feely is a NOAA Senior Fellow at the NOAA Pacific Marine Environmental Laboratory in Seattle, Washington. He also holds an affiliate full professor faculty position at the University of Washington School of Oceanography. His major research areas are carbon cycling in the oceans and ocean acidification processes. And he's a member of the GOA-ON Ocean Acidification Observing Network Executive Council. So Dick, I'll let you take it from here.
Well, thank you very much, Kalina. It's a pleasure and an honor to be here today, and I'm very excited to have 2 outstanding speakers today to give us presentations. The first one will be done by Dr. Leeching Jang on ocean acidification indicators on a global basis, and the second one will be by Dr. Jessica Cross on the marine carbon dioxide removal draft strategy that was just published last month. But before I introduce the first speaker, next slide, please. I want to let everybody know that we have just released the Ocean Carbon Dioxide Removal Survey. This is a subcommittee within the GOA-ON Executive Council that is focusing attention on marine carbon dioxide removal. And we developed this survey to let you help us understand how best we can serve the community and to find out what you think your needs are in marine carbon dioxide research relative to GOA-ON. So if you click on the right-hand image there, with your phone, you can get right into the survey. The survey itself only takes 8 minutes. I just took it yesterday. Very, very straightforward, and it'll be very, very helpful to our community to work together and to find out exactly what your needs are. So I encourage everybody to join the survey. With that, I will then now introduce our first speaker. Excuse me a second. Dr. Leeching Jang is an associate research scientist at the NOAA Cooperative Institute for Satellite Earth System Studies of the University of Maryland. Currently serves as the task lead of the Ocean Carbon and Acidification Data Systems, called OCADS, at the NOAA National Centers for Environmental Information. His research focuses on global carbon cycling and ocean acidification process, with particular emphasis on data management, quality control, synthesis, and development of ocean acidification indicators. Dr. Leeching Jang just recently published a paper on the ocean acidification indicators, and he's going to present his results now. I turn this over to Leeching Jang.
Hi, Dick. Many thanks for the introduction. I also want to thank the GOA-ON committee for giving me this wonderful opportunity to share my research with this group. Hello, everyone. Today, I will show you a new model data fusion product about the global OA indicators. Before I start, I'd like to thank Rick, Dick, as well as Tim DeVries for helping me put this talk together. I also want to acknowledge all the co-authors of my paper. I'd like to start my talk with a 40-second movie about atmospheric CO2. Enjoy. Hold on. So the highest CO2 level we recorded at Mauna Loa this year is about 424 ppm in May of 2023. And by the end of this year, I project the annual average this year is going to be about 421. If we compare that number with the interglacial average number of about 280, we are talking about an increase of about 50%. That's a very dramatic change for sure. So this slide shows you the carbon reservoirs on the Earth. We know that the atmosphere is not even close to be the largest reservoir at all. The largest carbon reservoir is actually the solid Earth. Actually, most of the carbon there is relatively inactive, and it only influences atmospheric CO2 through processes like rock weathering, sediment dissolution, and formation over a time scale of millions of years. If we are talking about active carbon reservoirs, the ocean is really the largest carbon reservoir that is actively exchanging carbon with the atmosphere. Because it's a vast size, the ocean contains about 40 times as much carbon as the atmosphere. Also because of the rapid exchange with the atmosphere, on a time scale of decades to millennia, the ocean really imposes a dominant control over the atmospheric CO2. That makes it really important to understand the carbon cycling in the ocean. Now let's look at what has been going on over the last 170 years. The Industrial Revolution started in about 1750, but from 1750 to 1850, over that 100-year period, the CO2 in the atmosphere only changed about 12 ppm. So that's a very modest change over a long time period. In 1850, this number is about 286. Then human activities like the burning of fossil fuel, deforestation, and cement production, is this bar, released about 660 gigaton carbon. That's enough to raise the atmospheric CO2 level by about a little bit over 300. So we're going to expect to see atmospheric CO2 of about 600 ppm. The good news is that about 60% of that fossil fuel carbon is being canceled out by the terrestrial and ocean biosphere. That's why we only see a relatively modest increase of about 130 ppm in the ocean. Now let's look at the cumulative change in the carbon inventories. Since the Industrial Revolution, the ocean has absorbed about 200 gigaton carbon. And some people are using the number like 185, but we really don't have that kind of precision. This represents about 28% of all the fossil fuel carbon. Of this CO2 that's being absorbed by the ocean, about 20% went to the surface ocean, and the rest of the 80% went to the subsurface ocean. The figure on the left shows you the distribution of anthropogenic CO2 between 1994 and 2007. If you think about this 200 gigaton number and compare it with the total carbon inventory in the ocean, today is 37,300 gigaton carbon, you would think that's a very small change, only 0.5%. Actually, Tim DeVries used a very simple 3-box model to show that during the pre-industrial period, the distribution was carbon between the ocean and atmosphere. That ratio was about 62. And today that number has decreased to about 42 versus 1. If we had simply doubled the CO2 emission over the last 270 years, and that ratio would become something like 7.3 versus 1. That's a really, really dramatic change. What that means is that we have already consumed much of the ocean's buffering capacity. Besides decreasing the ocean's buffer capacity, and this extra CO2 added to the ocean is also changing the ocean's chemistry. And after CO2 enters the ocean, a small portion of it would react with the water to form carbonic acid. And it will then dissociate and release extra hydrogen ions. This is really the problem because these hydrogen ions are going to consume carbonyl ions, which is a building block for many marine calcifiers. This phenomenon is called ocean acidification. The ocean's acidity have increased about 30% since the beginning of the Industrial Revolution. And under the high emission, low mitigation scenario, and the ocean's acidity is expected to increase by another 100 to 150%. That's a huge change. It really poses a threat to the marine ecosystem, especially for coral reefs and many marine calcifiers. I'm sure you would agree that it's really important to monitor this phenomena commonly referred to as ocean acidification. And by these numbers just show you that under just 1 decade of CO2 emission, this is average surface ocean water in 2010. Now we move on to 2020, that 22 microatmosphere extra CO2 is going to cause this much of carbonyl ion to, the carbonic acid to dissociate. And it's going to cause the carbonyl ion to decrease by about 7 micromole per kilogram. It's a very effective process, as you can see. So we have lots of OA indicators. I'm sure this audience is very familiar with these concepts. I'm not going to spend a lot of time for each of them. I just want to mention that a lot of times you would hear about 10 OA indicators. This is because acidity is commonly referred to, sometimes people report it as total hydrogen ion content, and sometimes people also report it as free hydrogen ion content. Also for the omega saturation state, we have aragonite and also have calcite saturation states for these different minerals. So why are these variables considered OA indicators? This is because when we add CO2 or remove CO2 from the system, these variables will change. And they are really good to indicate the change in ocean acidification, with one exception, which is total alkalinity. This is because when 1 carbonyl ion is being consumed, the system is going to release 2 bicarbonyl ions. We know that the carbonyl ion has 2 charges and bicarbonyl ions has 1 charge. So in the end, it cancels out with each other. Excuse me. If the system is that simple, our life would be so much easier. Unfortunately, temperature really makes the system really, really complex. A lot of these OA indicators are highly temperature dependent. This slide, I just want to show you when temperature changes, how these OA indicators would respond. In this case, I'm using an average surface ocean water like this, and increases temperature from 20 to 25 degrees. In this process, the bicarbonate ion would dissociate, releasing extra hydrogen ions and the carbonate ions. And the water will also dissociate. This is actually a very important contribution if you look at these numbers. And then a lot of these extra hydrogen ions would be consumed by borate. And some of them would react with the bicarbonate to form aqueous CO2. This is why when temperature increases, the CO2 increases. Actually, what I just described is the chemical speciation is just one of the processes affected by temperature. Another process is the CO2 solubility. When we increase the temperature, its solubility changes dramatically as well. Actually, it changes the CO2 by twice as much. Basically, from the tropical area to the polar regions, the temperature change alone would cause the solubility to be different by over 100%. So when temperature increases, the PCO2 increases dramatically. The pH also decreased by about a 0.08 unit. That's about a 20% increase in acidity. What's interesting is that in this process, the saturation state, instead of decreasing, is actually increasing. This is because of this equilibrium. When bicarbonate ions dissociate, we release extra carbonate ions. That's an increase of about 1%. And we also have the apparent solubility product decreased by about 2% with the temperature increase. So the saturation state increases by about 3% in this process, even though the ocean is getting more acidic in this process. So is there a way we can show the relative contribution of these two effects? One is about adding CO2 and removing CO2. The other is about changing temperature. I think a really good way of thinking about this is to imagine you have a parcel of seawater at the Arctic, for example, at 0 degrees. Now you move that water slowly towards the poles, so slow that it's going to have enough time to get equilibrium with the atmosphere. So in that process, you're going to lose CO2, PCO2 is going to decrease. At the same time, the increase in temperature will elevate the CO2 as well, as I showed you in the last slide. So as you can see, for all indicators like PCO2, hydrogen ion content, and pH, the temperature effect is gigantic. It almost can counterbalance the entire change that's caused by the changes with the DIC to the system. In comparison, for carbonate ion and aragonite calcite, their change by temperature is much smaller. So we need to be very careful when we use PCO2 and pH as indicators about the calcification risks. So we know models are really good at simulating the oceanographic processes, but the models are really a bunch of mathematical equations. They are not good at providing the best baseline conditions. Observational data, on the other hand, provides the best baseline conditions. This makes it really important to use the latest observational data to correct the models. These authors did exactly that several years ago. They combined one GFDL model called the ESM2M with the 6th version of the SOCAT data product and demonstrated the decrease in pH and the increase in hydrogen ion and also increase in reveal factor, which is an indicator of ocean's buffering capacity. 4 years have passed since that study, and now we have all these next generation models. These CMIP6 models are simulating more oceanographic processes, and they have better resolutions. So we should move on to these models for sure. Another huge improvement is that this time, instead of picking one of these models, we are going to use all these models. We basically went to all the CMIP6 models and identified 14 Earth system models with distinct biogeochemical cycles. We're going to use all these models to constrain the final results. We now also have the new emission scenarios. The old RCP scenarios have been not being used anymore. Now we have moved on to the new shared socioeconomic pathways. I want to emphasize that these are not apples to apples. They are really different things. They are apples to oranges. They have very different projections in terms of CO2 and other greenhouse gases, as well as forcing agents like aerosols. For example, under the 8.5 scenario, the RCP and SSP difference is about 200 ppm for the atmospheric CO2. We also have updated observational data with more better data quantity and better spatial coverage. We should take advantage of them as well. This is what we did to the observational data. We combined all of these observational data products and then adjust their carbon system variables to the 2010 level using Brandon's algorithms. We then interpreted them onto a 1-by-1 global surface ocean grid. And we also use proxy-based values from ESPER and the World Ocean Atlas based temperature, salinity, and oxygen, and use them to QC the graded data, especially in areas with very little observational data coverage. Once we have all the observational data ready, we use it to adjust the model output. Here's what we did. We have a 1-by-1 global surface ocean grid. At each of those grid points, we would compare the model output with the observational data in 2010. If we find an offset, we are going to apply that offset to the entire time period from 1750 all the way to 2100. We do that for all of the models, all the 14 Earth system models, and for all of the 5 emission scenarios. Once we multiply everything, you will understand why that really slows my computer down. We also removed the model drift by using the pre-industrial control. We basically get all these values from the models and apply it here. So the panels on the left column shows you the raw model output. These are area average values from 1850 to the end of this century. And those panels in the middle column shows you the area average values after we adjust those values based on observation and also based on the pi control. As you can see that after the adjustment, these models agree with each other much better than before that. In the end, we decided to use their median values for the final results. This time, instead of just select, sorry about that, a few of them, we decided to release all of these OA indicators. Here, I just want to show you one of the OA indicators. We have values from 1750 all the way to 2100, and these are on a 1-by-1 global ocean grid. And these data are stored as NetCDR files, and I can show the link later on. This plot shows you the temporal evolution of these OA indicators. These are their area average values. As you can see, overall, these models agree with each other pretty well. The only exception is the total alkalinity. They are all over the place. The good news is that we are talking about a very small y-axis of only 60 micromole per kilogram to start with. So it's still relatively a small change. I really hope the modeling community could make these models agree with each other better for the alkalinity as well. So I'm ready to share the slides with you all after the presentation. These are all the links. And for the paper product, I also recommend you to play with this visualization tool. Basically, these are pre-plotted maps. And you can basically go to one of the year, one of the emission scenario and see the maps for all these OA indicators. I also can't resist sharing these two really exciting papers about the surface OA indicators. The first one is led by Dick, and this is showing that the keto change of OA indicators based on actual observational data. The second one is from Nikki Gruber's group, and they are using a machine learning data product to show that the keto change. And their results actually from these papers agree with each other really well. I also want to emphasize the importance of subsurface ocean. And what I just showed you, everything is about the surface ocean. But recent studies have shown that the ocean acidification is actually happening faster in the subsurface ocean near the surface, near the mixed layer depth. As you know, the surface CO2 is strongly controlled by the equilibrium with the atmosphere, which is largely prescribed by the same trajectories, making it a relatively easy job. In comparison, the subsurface OA projections are going to be different by a larger magnitude for sure between these models. That's why we wrote a proposal and try to tackle that issue in the next step. I also want to use this opportunity to thank my founders, NOAA's Ocean Acidification Program, and NOAA's National Centers for Environmental Information. Also, NOAA's GOMO program supported a lot of my co-authors on this work. I also want to emphasize that this product is built on the shoulders of 14 Earth system models and 3 observational products, and also the World Ocean Atlas. I want to acknowledge the contribution of all those people behind these products. That's all. Thank you for your attention.
Thank you very much, Li-qing. That was an excellent presentation. And we will want to get back to you during the question and answer period. It's these data sets that will help us to evaluate and understand the changes that'll take place in the future when we get into marine carbon dioxide removal. And our next speaker, Jessica Cross, will explain the strategic plan that we have put together within NOAA and recently published on marine carbon dioxide removal. Jessica is a research scientist at the Pacific Marine Environmental Laboratory and works at the interface between research and engineering communities to develop new tools to explore how our oceans support sustainable development and contributes to climate risk assessment. As an oceanographer with NOAA, she leads the agency's carbon dioxide removal task force and manages the carbon system observing, research, and development for Alaska and Pacific Arctic regions. Jessica, I'll turn it over to you.
Thanks so much for that kind introduction, Dick. And hello, everyone joining us online across your many various time zones. Good morning, good afternoon, good evening, depending upon where you are. I've been asked to come in and chat today a little bit about carbon dioxide removal, which is a topic that's certainly growing in the global climate conversation, and maybe link that a little bit to the priorities of GOA-ON. So we'll start with a little bit of background. We'll jump into some current activities that are ongoing today, and then hopefully leave you with opportunities to find out more depending upon what part of this you're actually interested in. So first, a little bit of background. Nearly all of the different scenarios, climate scenarios that are in the IPCC, the most recent IPCC report, AR6, that limit warming below 2 degrees Celsius require carbon dioxide removal of some kind. And in fact, there's only one major scenario that didn't, and that was the one that was specifically designed not to, and was designed not to show how difficult it would be to meet all of our climate goals without CDR of some kind. So you can see that in this bar graph here at the lower left-hand side, it's showing 3 different groups of scenarios. In the first set of bars, that's 1.5 degrees Celsius, scenarios that limit warming to 1.5 degrees Celsius with limited overshoot. The second set of bars represents scenarios that limit warming to 1.5 degrees Celsius with a high degree of overshoot. And the third set of bars is a group of scenarios that limits warming below 2 degrees Celsius. And what I want you to notice here is that these blue bars for each set of scenarios are at almost 100% for each different set. Furthermore, there are both blue and yellow bars in each particular set of scenarios. The blue bars represent a form of carbon dioxide removal called bioenergy with carbon capture and storage. And the yellow bars represent a CDR strategy called direct air capture and carbon storage. So BECCS and DACS for short. The gray bars, which are small in this particular visualization, represent enhanced weathering, another CDR strategy. But again, what I want you to notice is that all of these scenarios, almost all of them include some form of BECCS, DACS, and enhanced weathering in order to meet our climate goals. If you're interested in a little bit more of what the IPCC has to say about carbon dioxide removal, they've actually put together a little primer and fact sheet, which you can just Google very easily for yourself. In order for us to develop the amount of CDR that we know is going to be necessary, it's going to require a lot of energy and investment from the global community. In order to meet, these goals that I showed on the last slide, we're going to need to extract about 10 gigatons of carbon dioxide from the atmosphere every year, starting in about 2050, and increasing to about 20 gigatons of carbon dioxide from the atmosphere from 2100. And what that means is that from now, we're going to need to hit about 6% annual growth. For those of you that have any kind of investments with banking, you know that 6% is a killer return on any kind of investment that you might want to make. GDP, we're happy if it grows somewhere between 1% and 2% every year, right? So 6% annual growth is a massive amount of investment and growth for any industry to try to tackle. It's unicorn status, right? So what that means is that the banks have decided that this is a killer opportunity for investment. If we definitely know we're going to need all of this carbon removal, they absolutely want to be there for 6% return, right? And so companies that are selling what are called advanced commitments, which is, the promise to deliver some tons of carbon removed in the future, they get paid for it now, so they can use that investment to develop these technologies that will help them remove carbon in the future. That sort of model in industry is growing a whole bunch. And so you can see here on the left, some of the logos from folks that are either providing or selling carbon credits. And what this line plot on the right-hand side shows is the amount of advanced market commitments in terms of tons purchased from, over the course of the last several years. And just in May of this year, JP Morgan bought 800,000 tons of advanced market commitments. And you can see it's produced this massive hockey stick in the diagram. So the global investment community is certainly interested in what might eventually be a 6% annual return. So that begs the question, if there's this much, human need and this much energy from the financial sector, that's a real recipe for move fast and break things. And so the global research community is interested in these kinds of questions. Can it actually be done, for one? And second, can it be done in a way that is safe, sustainable, and fair in a variety of global settings? So even though, we tend to lump all removal together as one kind of product when we're talking about it in these big generic terms, the truth is that there are very many ways to remove carbon from the atmosphere, including methods on both land and in the ocean and in our coasts. I'm not going to get too deep into each one of these methods today, but I'll point out that there are really 2 primary ways to remove carbon from the atmosphere. In one, you can use photosynthesis, whether by growing forests on land or phytoplankton or macroalgae in the ocean, or maybe mangroves at our coasts. On the other hand, you can use chemistry, and that can either be things like alkalinization or enhanced weathering, or it can be more engineered chemistry like direct ocean removal or direct air capture, for example. All of these different chemistries help us remove carbon from the atmosphere in an inorganic way. So you have photosynthesis and you have chemistry. The truth is, for all of these different kinds of methods, a lot of them have really high costs. That can include high energy costs. Direct air capture takes a lot of energy, for example, to power a direct air capture plant. Some afforestation methods and agricultural methods require a lot of water or land use, and that's true especially when scaled. So this image is from a paper. You can see the citation over here. From a paper that identified some of those pressures that really scaling each one of these methods of removal might place on global systems, whether it's electricity input and heat, which you can see in the top two panels, or things like land use and water use in the bottom two panels. That's definitely true for afforestation and BECCS. And then you can, of course, see that DAC methods require a lot of electricity and produce a lot of heat. To really put that in scale, it's really hard to look at those bar charts and say, okay, well, what does that mean? You have high water or energy or land usages. Let's do a quick thought experiment that's based on a couple of citations that you see here. If you really wanted to remove 10 gigatons of carbon dioxide with any one of these methods, let's say for alkalinity enhancement, where you're adding alkaline or base minerals to the oceans, you'd need to dedicate half the world's cargo ships to it. Think about what that would mean for your Amazon delivery times if we just lost half of our global shipping capacity. If you wanted to do that with direct ocean capture, that means dedicating 80% of our global energy output to it. Imagine trying to reduce your electricity footprint by 80%, not your carbon footprint, your overall electricity footprint. Get to charge your phone once a week instead of every day. And for macroalgae, just to grow enough kelp to remove, a much smaller amount than 10 gigatons of carbon dioxide from the atmosphere, you need a 0.5 kilometer wide belt of kelp around the coastline of all of the world's oceans and islands. Much bigger than that, actually. And that's based on an estimate from the national academies as well. So when we talk about trying to remove 10 gigatons from the atmosphere with any one of these particular methods, you can really rapidly see the strain that it might place on global systems. So we're starting to think now that the more methods of carbon dioxide removal we have, the easier it's going to be on Earth systems. And that's what you see imaged in these plots right here. So across the top, this includes different portfolios of carbon dioxide removal, starting with, just a free market scenario on the left-hand side and building towards smarter portfolios in climate policy on the right-hand side. And so the more colors you see, again, in this top bar, the more different methods of carbon dioxide removal we're using. And then on the bottom row, you can see that over these different scenarios, the smarter the portfolios and the smarter the climate policies you implement, overall, you reduce the energy demand that's associated with the portfolio of carbon removal that you're looking at. So what we want to do is distribute these stresses, distribute these different strains as best we can, as equitably as we can across the global system. And that's going to help us meet our sustainable development goals. Maybe we can grow enough kelp, or maybe we can, grow enough forests in order to, or maybe we can, grow enough artificially grown phytoplankton for bioenergy, carbon capture and storage for BECCS, but we'd starve some people in the process simply by displacing agricultural outputs. And we don't want to do that. We want to be able to meet our sustainable development goals in addition to removing enough carbon from the atmosphere to limit the negative impacts of global warming on human and ecological systems. So that then begs the question, which of these methods should we be studying first? In an analysis that we recently did at NOAA, we looked at things like, what's eventually going to be cheap, what is really going to be effective, and more than that, what's going to be durable. We want to make sure that the kinds of carbon removal we're developing are actually going to last for a little while. And so you can see in the 4 quadrants imaged in this particular plot, there's cost on the x-axis, the effectiveness in terms of the tons carbon removed per year on the y-axis, and then the size of the dots are the durability. So what you're looking for if you want a really good method of carbon dioxide removal is something that's cheap, effective, and durable. That's in the upper left-hand quadrant. And you can sort of see the big black dot in the upper left-hand quadrant here is alkalinity enhancement. I do want to take a minute to emphasize that this is a static view and that over time, our hope is to be able to pull all of these methods more into that upper left-hand quadrant, balancing, the need for technology development, again, to sort of get us into that cheap, durable, and effective quadrant for all of these different methods. But some of them are ready to go right now. That being said, there are a ton of challenges with trying to implement carbon removal, despite how theoretically ready we might think we are. The truth is that we are not very good at estimating additionality, or the actual, what that means is the actual capacity of any of these different climate solutions to actually limit the amount of carbon dioxide that's going into the atmosphere. Even when we're talking about offsetting traditional fossil energy with renewable energy, we can only verify the additionality of about 34% of those kinds of products. If you come down to carbon removal technologies, it's 0, at least in this particular analysis from 2020. In 2023, Climeworks says that a third-party auditor has finally verified the amount of carbon that it's removed and its additionality. And you can find that at the link here. So that may be changing, but the point I want to make is that we've got a long way to go if we want to understand how to monitor and verify that these removals are actually having an added benefit in the Earth system. Another key challenge that we have with developing carbon dioxide removal is estimating and valuing ecosystem and human impacts. Like I said earlier, we don't want to get all of the carbon removal we need at the expense of starving a whole bunch of people. We'd like to do it in a more equitable context. And that's especially true when it comes to thinking about ecosystem impacts. What you see imaged in this chart on the right-hand side are different methods for carbon dioxide removal here on the left, and then across the top, different ways that these carbon dioxide removal methods might impact ecosystems in either positive or negative ways. And what I want to point out to you is that there is no method of carbon dioxide removal that won't have an impact of some kind on its local environment. And so we really need to be pouring as much energy and research into understanding these ecosystem impacts as we are pouring into the capacity to monitor and measure these actual removals so that we know collectively what the cost-benefit analysis is going to be for each of these different methods. Especially since I'm talking to GOA-ON here today, I thought I'd take a moment to talk about one particular co-benefit of removing carbon from the atmosphere, and that might be the reversal of ocean acidification. But I want to place a big caveat on that right now. The truth is that even if we remove a lot of carbon dioxide from the atmosphere, or even if we're talking about ocean carbon removal, if we remove a lot of carbon dioxide from one spot in the oceans, the truth is that it's not going to have a big impact on ocean acidification without what there's also steep parallel emissions reductions, because we're just going to soak all that carbon dioxide right back up, right? In fact, it's very likely that even in the most ideal scenario, CDR could pause, but not likely reverse existing acidification damage. So if you do as much carbon dioxide removal as you can from the oceans, you can probably get a rate of removal that's about the same as the rate of the annual absorption from of anthropogenic CO2 from the atmosphere. You can balance it out, which pauses the progression of ocean acidification, but doesn't run the process in reverse. By contrast, you could use some of the same chemistry methods or the same biological methods to remove carbon dioxide from the ocean. And if you do it at the subsurface, you might be able to alleviate some of the impacts of ocean acidification. That's, some of the experimentation that's going on in the coral reef community right now. But unfortunately, because that happens at the subsurface, you don't have the contact with the overlying, air-sea interface, which means you're not removing carbon from the atmosphere. So while it's the same method, it's not removing any carbon from the atmosphere. You can't really do carbon dioxide removal and ocean acidification mitigation at the same time. So now we're starting to think about scenarios where we might be able to deploy carbon dioxide removal methods in the same areas as we want ocean acidification, and just admitting that these are going to be two different parts of the same process. So if you have an alkalinity enhancement plant, for example, hey, yeah, we want to get a bunch of that alkalinity at the surface in order to remove carbon from the atmosphere, but we also maybe want to do some subsurface injection of alkalinity to mitigate the impacts of ocean acidification as well. Maybe there's an opportunity to daisy chain these kinds of climate mitigation opportunities. So for us as researchers, what kind of research projects are going to end up having the highest impact for us? What do people need to know in order to get this technology off the ground so that it has the best benefit that it possibly can? Safe, sustainable, and fair, right? The way that people make decisions is with these scalable interdisciplinary maps. So essentially what we want is Google Earth for climate removal or for carbon removal, right? Can we zoom in on a particular spot and say, hey, is a particular method of carbon removal going to be a good idea right here? Or is it better to do it over there? Those are the kinds of maps we're looking at. And in fact, those maps already exist for some other purposes. At NOAA, our National Centers for Coastal Ocean Science work really hard to produce aquaculture planning maps that balance not just where, an aquaculture farm might be successful, but where it might not compete with other types of marine use projects, whether that's, impacting them over the top of oil and gas leases that have already been issued, or places where there are submarine cables, right? I'm very fond of saying that you can't fish for crab in a kelp farm. That's two really important growing industries in Alaska that are kind of mutually exclusive. So you're going to need, in addition to, understanding what ecosystem impacts are, you're going to need qualitative information, qualitative spatial information like this in order to do adequate habitat mapping and siting for some of these projects as well. So these scalable interdisciplinary maps are going to have quantitative layers as well as qualitative layers that help people make decisions based on multiple different kinds of information. So at NOAA, we recently published a research strategy to help define how we think we might be able to move the carbon dioxide removal research forward based on our mission. You can find out more about it at the QR code here on the screen. If you're a researcher and you really want to dig into the specifics and details, the white paper itself, I think, is about 60 to 70 pages long. If you're not really feeling that much of a commitment, again, on that same website that the QR code is showing on the screen right there, you can find a 2-pager that has a pretty good summary in it. Overall, really one of the key findings of this report, I've already showed a handful of them in the presentation so far. One of the key findings of this report is imaged in this table right here, which just shows the current assets that NOAA has and how we might be able to develop them for CDR going forward, and then what the overall impact might be on the overall deployment and CDR research field. So that's going to include optimizing our observing networks, creating new modeling and projection packages that help us understand what CDR might look like in the future, both in terms of impacts on the global carbon system, as well as in terms of impacts on global ecosystems. We're going to want to better understand environmental impacts, and that includes laboratory perturbation research, just as the type that we've done with ocean acidification thus far. And then as well, we're going to need, those scalable interdisciplinary maps. And so that includes, rolling all of that information from our observing, our modeling, and our environmental impact research into decision support tools. So what's happening right now at NOAA is that we're trying to get off the ground here, and through the National Ocean Partnerships Program, we were able to sponsor a big call that I know that several of you participated in on the line here today, and we thank you again for your proposals. While the call is closed, we do expect to announce the successful proposals in September or later this fall. You can view the full NOFO if you want to read it at the QR code that is here on the screen. So that NOP call is just, a small part of the investment that's going to be necessary to help us meet our climate goals. We're talking about 6% annual growth, right? So in addition to all of the money that the banks are pouring into private companies, governments are also going to have to pour a lot of investment into CDR research as well, especially at this early phase before, venture capital might be willing to invest in some of these high risk, high reward projects. So the bar chart that I'm showing here on this screen showcases that for the US, the average annual renewable energy investment that we make, that's the top bar right here. And then comparing that to a proposed 20-year investment in carbon removal, as well as a 10-year investment for ocean CDR. And so overall, that totals to about $65 million a year for 20 years. And that's really small compared to the amount of money that we invest in renewable energy. So I know we can do it. In terms of actual US dollars that hit the street to support the next fiscal year, to support FY24, there were $119 million that were advertised just for projects starting in FY24. And that exceeds, that 119 million number exceeds the necessary $64.5 million number by about 60%, which means that the government is interested in helping us meet these goals, right? At least in the United States. One of the key challenges is that we've now signed a debt ceiling deal, which may limit the amount of future investment. So that additional 60% might have to last us a couple of years. So let's not get too excited. But it was really nice to see the momentum, certainly in making these investments over the course of the last several years. CDR has been a focused investment of every major piece of legislation that's been passed since 2020, and that includes the last 2 administrations in the United States. But this is GOA-ON. I don't want to talk too much about the United States. And so I want to point out to you that there are multiple groups that are trying to bring carbon removal, equitable carbon removal, safe, sustainable, and fair carbon removal to the global south, as well as the rest of the globe. You can find a link to the Global Carbon Partnership in the QR code that's in the upper right-hand corner of this particular image. I also want to point out to you that there is an absolutely excellent chapter in the CDR Primer from Jennifer Wilcox. Again, you can find the link in the upper right-hand corner, the QR code there. I encourage you to take a photo of it that globally maps different CDR opportunities. And so that includes these daisy chaining opportunities that we've been talking about before. Where do you have the energy generation to actually support direct air capture? Where do you have the source minerals that might support enhanced weathering, mineralization, or alkalinization, right? Tons of great analysis there. I wish we had time to talk about all of the different maps that are present in this chapter. Highly encourage you to go check that out. The last thing that I'll say again is that, while we as researchers historically, try not to collaborate too much with private industry, the fact that there's this much money involved means that we have to start doing a little bit better with public-private partnerships. Again, this, bar chart, this line plot that you see on the left-hand side is the exact same one that I showed you before. And then I just pulled a couple of headlines from major papers and journals and magazines there. If we're talking about a one-way bet for hedge funds or $1 trillion business, we're going to have to learn how to talk to private industry about the kind of work that we do. There are a number of companies that are already springing up as private data providers in the carbon removal space that need guidance from scientists on how to actually verify that carbon removal has happened and to understand how to discount uncertainty. Can you imagine private industry is suddenly interested in uncertainty, especially relevant for the presentation that Li-qing just gave, And then as well, we want to understand what the potential environmental impacts are, because companies are really not interested in creating a massive PR problem for themselves. And so they're really looking to these groups and to us as scientists to help them understand responsible deployments. So that wraps up the presentation for me. I understand that we're going to head into a little bit of a discussion period, and I look forward to taking your questions.
Thank you very much, Jessica. This was indeed an excellent presentation and a really good overview of the challenges that are ahead. I want to open it up for questions now, and we'll turn it over to Kalina. Kalina, can you give us some of the questions from the audience?
Yes, so unfortunately we only have time for one. Oh, okay, I guess we can go a little bit over time, but we recognize that it is near the top hour, so if people have to drop off. We have lots of great questions from the chat, and I'll start by reading this one, which overlaps a little bit with both presentations. So in Leeching's presentation, he indicated 10 ocean acidification indicators and cautioned against focusing on total pH and PCO2. And so this question says, is there a way to weigh these 10 indicators to provide a meaningful ocean health index indicating the potential for problems from ocean acidification? And it leads to further questions related to, is there a value in diminishing ocean acidification by alkalinity enhancement? And if so, which OA indicator should be used to quantify the value of such a process?
Yeah, let me answer that question a little bit differently, and I think it's one of the most appropriate questions to be asking. I want to address this question directly to Jessica. Jessica, you have a good feel for the present day global ocean acidification observing system and carbon observing system. From your perspective as understanding how we will probably be enhancing our marine carbon dioxide removal approaches, how would you utilize the indicators that Li-qing has just shown us in a way that would effectively at least begin the process of doing the monitoring and validation? What's the strategy you think needs to go forward from this point onward in terms of monitoring and validation?
Right. One of the things that I think that to kind of obliquely answer your question, one of the things that I think is going to be necessary is, again, we need to get better at spatial analysis. So rather than relying on one of those indicators, I want to know how to stack all of those indicators on top of each other and weight them according to what you want to know. So think about when you try to make a decision about a new country or a new state to move to, right? You're going to be thinking about things like, is it close to my family and will I be able to have a job, right? And maybe for some people, some of those things are more important to each other. Maybe you don't necessarily want to live too close to your family because you'll get asked to babysit all the time. That definitely happens to me. Maybe you absolutely do want to live close to your family because you have aging parents that you need to be caring for, right? Or maybe you're a new parent that sort of needs that support system. So again, the way that these indicators are valued might be different to different people. And certainly, in a global context, we can think about some of these indicators and how they'll help us understand science, but really the application of CDR is going to be place-based. And so you need a way to evaluate a particular place for things like ocean alkalinity enhancement. And again, that's going to depend on a lot of different layers and different weights for layers in each place rather than each one. I know that that's not a satisfying answer, but we do need to get better about these decision-making matrices, is what I would say. We need all of them, and I want to know how to weight them appropriately.
And do you think there's a role for satellite measurements in this regard so that we could do not only the modeling, but the synthesis of satellite data to get at these global perspectives and anomalies within that global perspective? How would you approach that?
Sure. So remote sensing is certainly something that private industry is very interested in. The private data companies that I showed you earlier, a lot of them use freely available satellite data in order to be able to push these products to other places. So certainly there's a global infrastructure for consuming and distributing remote sensing data. Again, those global perspectives are really nice and valuable, and given the proliferation of things like Starlink and new interest in things like, oh man, I just had it on the tip of my tongue. The new satellite that NOAA is gonna put up into the air. There's a G in the acronym. Shame on me. But anyway, a couple of the new satellite sensing packages that are going to be developed for ocean color and different things like that. I think we have the potential to do monitoring of some CDR projects and to be able to incorporate remote sensing data into this kind of new perspective. That being said, I am skeptical of anybody that says that they can directly monitor carbon dioxide from satellite packages. That is certainly something that we need to do a little bit better. But in terms of ocean color, alkalinity enhancement in particular, there's a danger of producing, we're starting to learn that maybe less of a danger than we thought, but a danger of producing what are called white ocean impacts, of over favoring coccolithophora production, for example, over other types of phytoplankton production that might have occurred if you hadn't enhanced alkalinity in a particular region. And satellites are really good at finding coccolithophora blooms. Simultaneously, there's new interest in things like tracking harmful algal blooms, either fluorescent green or maybe red algae as well. And ocean color satellite products can be really, really good at tracking that. There are also new satellites that are capable of tracking PM 2.5. And so as we mine and grind carbonates for use in enhanced weathering projects, in mineralization and alkalinization scenarios, this might help us understand how much of that material is actually ending up in the air where it might cause adverse human health impacts. So I definitely think that there are roles for satellite remote sensing that can be applied now. But we have to be careful as we develop new sensing capabilities in the future. We want to make sure that we're actually monitoring CO2 and developing those kinds of packages. I don't want to oversell the capabilities that folks have for satellite remote sensing of carbon parameters right now.
Li-qing, I want to bring you into this conversation. Where do you see the indicators going, and how do you see that enhancing our efforts in marine carbon dioxide removal?
Yeah, in terms of the satellite discussion, we are actually finishing up a project with Brandon Cotter and John Sharp. Basically, we use machine learning to connect observational data with lots of satellite parameters. And then even though if you look at one of the values, they could have a large uncertainty, but we are able to show the temperature change really well. I think it's very promising in that direction. And coming back to the indicators in terms of the impact to the marine ecosystem, it really depends on what you are looking for. If we are looking for whether we are looking for the calcification rate, or we are looking for some other parameters, like if the ocean is getting noisier, that might be directly linked to its acidity. In that sense, pH and PCO2, they are totally fine indicators. But if you're using these indicators to indicate the calcification risks, we do need to realize the large temperature impact, especially when we compare the OE conditions at different regions with a large temperature difference. In terms of temperature change, excuse me, if there's not a larger temporal SST change into the future, it might also be okay using PCO2 and pH to indicate OA. Thank you.
The other question I wanted to ask you both, so either one of you jump in, what about the new approaches with BGC Argo? Do you have a vision on how these new technological approaches can help us to understand the impact of any particular approach to marine carbon dioxide removal?
One of the things that we definitely know we're going to need in order to measure, any kind of removal directly is a solid baseline. If we don't know what the baseline carbon flux is in a particular region, you have nothing to measure against. And so programs like Argo help us resolve that baseline better. No question about it. And so the better the Argo program we have, the better our baseline of, regional as well as global carbon flux is going to be, which helps us assess additionality at all of these different kinds of scales. So I know that Argo is going to be an important part of the conversation going forward. Li-qing, what about you?
Yeah, I agree. Basically, every time when I look at the observational data products, we have a big blank area in the Southern Hemisphere. That's the region that we actually have Argo data. I really think what we need to do as a community is to create the products for those uncrewed platform data. And once we QC them and create a product like that, and then we use those products to supplement and existing products like the SOCAT and GLODAP, and then really help to improve the uncertainties in these data sparse regions like the Southern Hemisphere. I think there's a lot of potential there.
Helena, I'm going to turn it back to you for a moment. Are there additional questions from the group that you want to bring to bear into this discussion?
Yes, and I feel like you were touching on this a little bit, but a few questions were wondering about how you are all engaging with and how people can get more involved with from Indigenous communities, early career researchers, as well as the Global South to incorporate their perspectives on these subjects.
Indigenous communities, early career researchers, and folks from the Global South is what I heard. So I'll take them one at a time, even though I think what I have to say can apply to all three groups. So first, Indigenous communities. From my work in Alaska, I know that there's concern that ocean carbon removal and coastal carbon removal might end up being the next great land grab. Folks are really worried that traditional fishing areas are going to be the next place that big business comes in to, sort of take over territory and leases and stuff like that, because they're simply better funded and it costs money to try and be able to get permits and things like that. If a tribe decides that they want to lease their land to a private corporation, they also want to be extraordinarily well informed, which just requires a big educational effort, either to help tribes take advantage of these opportunities themselves or to evaluate their partners. So there's a group in the Pacific Northwest that is trying to build this kind of education pathway for tribal voices that includes, British Columbia all the way down to Northern California. Really trying to put them in charge of the conversation about what happens on their land and in their waterways. That kind of model, I think, is going to be necessary. Again, coming at it from the perspective of helping tribal and indigenous communities exercise their rights in the way that they see fit, right? Rather than coming in and telling them what to do, you want to give them enough information that they can make their own decisions and exercise their own rights appropriately. Early career researchers, if you're here, you're doing it. Learn as much as you can. There's going to be an exploding demand for the kind of skills that we develop as researchers in GOA-ON. Whether you are measuring the ecosystem impacts of ocean acidification or whether you just know how to use carbon sensors, that is you are going to be in demand from a big emerging industry. And so my also encouragement to you would be to, step out a little bit during your educational career in graduate school or in college to understand what the private industry landscape looks like. Join groups like Open Air or Air Miners that sort of introduce you to a variety of different companies that are working in this space, because the more exposure that you have to the different roles that you might be able to play in the carbon removal industry, the more you'll be able to understand, where your skills and strengths might be best applied. The last one was expanding to the global south. One thing that I am heartened by is the number of opportunities in the global south for these daisy chaining kind of industrial ecologies, right? Where we have the energy, the source material, the potential for underground storage and things like that. There are so many places in the global south that are really going to be ideal applications for some of these carbon removal technologies. And the mapping efforts that emphasize that, again, check out that chapter in the carbon dioxide removal primer. It's free online. It's also beautiful in terms of graphic design, so it's really enjoyable to read. They really paid a great artist to help them out with it. Anyway, check that out, sort of look at what the opportunities are in the global south. You know, some of the same comments that I made about indigenous communities as well can be applied in this context, right? What we're looking for is safe, sustainable, and fair. So while there may be a great opportunity to deploy these carbon removal technologies in places in the global south, we also want to make sure that we're not doing that just to find out how bad for the environment it's going to be before we deploy it in the global north, right? We want to be responsible with the environment in the global south, just as we are responsible for the economic development in the global south as well. Again, check out those maps in the CDR Primer. There's a bunch of different ways of evaluating that. It's going to be place-based. You know, any kind of implementation of CDR is going to end up being place-based. So those place-based perspectives and strategies are going to be extremely important. And, you know, really emphasizing not just, you know, the math, the quantitative aspects of carbon removal, but also the other aspects as well is going to be a critical part of this conversation. So getting that spatial analysis, those scalable interdisciplinary maps with multiple different kinds of qualitative and quantitative layers, I think is going to be essential for making those kinds of decisions.
So before we end this, I wanted to ask both you, Jessica, and Li-qing, if you'd be willing to share your presentations with Kalina so that we can get this into the web through the North American Hub website, and make sure that this will be available to all the participants today. These were two excellent talks, and the information you provided is extremely worthwhile, and we really would appreciate it. I want to thank everyone for your participation today. This has been an outstanding North American Hub webinar. There will be future Hub webinars throughout the remainder of this year and into next year. And I want to offer the opportunity for those of you who are interested in this is to get in contact with the Global Ocean Observing System leadership and offer your services to help out with the subcommittee, for example, and participate. The more participation we get, the better off we will be. And this is a really important topic, and the GOA-ON community really wants to make sure that they're providing you with the information that's most useful to you. So thank you very much, everyone. I appreciate all your participation today, and I really want to thank the speakers today for just an outstanding job.
Thank you, Dick, for asking such excellent questions. I had canned responses for none of those. It's so exciting to be able to sort of expand the conversation in new ways.
All right,
Thank you, everyone.
Appreciate the invitation.
Thank you, everyone. Thank you for joining.
Bye.